Start recording. Okay. So yeah, welcome everyone. I'm Jeremy, working on XTDB. Today, in advance of our launch of V2, we are speaking with Arjun Narayan, who is joining from New York. And on the call, we also have a bunch currently of the XT dev team. So Arjun and I spoke first a couple of months ago, must be, but I've been following Arjun's work on Materialize. Got the t-shirt here. For a number of years, because it's always been sort of an exciting example of or glimpse of how far XT can go in terms of making splashes out in the wider world. But yeah, Arjun, now you're at Amplify, right?
Yes, that's right. I'm a venture capitalist at Amplify, where I invest in technical products of all shapes and stripes, but of course, including databases.
Great. Well, yeah, you're in good company. So yeah, as I said, we've got a bunch of the dev team on the line. James, in particular, do you want to just introduce yourself quickly?
Yep, I'm James Henderson. I head up the engineering team for XTDB. I've been working on XT for about 6 years now. I think so. Before that, I worked on a lot of systems that had problems that I eventually boiled down to all being related to time. And so rather than implementing half of a bitemporal database every time, I decided to come and write a bitemporal database.
Yeah, I might have had a hand in luring you over, but yeah, it's been a fun journey to get here. And Arjun kindly volunteered to sort of run the next 45 minutes, so we have quite a tight time window to work in. So Arjun, you want to throw some questions at us?
Yeah, so one of the interesting things that I found about databases is that there's just so much history and so much context, and even experts or people who know a lot about databases don't know everything, right? So they don't know the complete space. You don't just have your OLTP databases and your OLAP databases and your time series databases, but there's lots of flavors of all of these. It was quite late. I mean, I did a PhD in distributed systems. I worked on Cockroach DB and the scale out OLTP database before starting Materialize. Um, and it was fairly late in the game. You would think I would have come across, for instance, one of the most successful database products commercially. Also, by the way, growing up in New York, sorry, not growing up, but going my career in New York. Um, you would think I would have come across KDB Plus, but it was actually, I would want to say, like a decade before I really discovered that one of the most interesting databases in the history of databases, um, you know, widely deployed across Wall Street, used in pretty much processing most financial transactions. And yet it was something that I was quite unaware of. That was my first sort of entry point to understanding that there are quite challenging problems that require and benefit from the structure of having a database that has a formal semantics and a query language to help process the data in areas that are very large but still quite unknown to your average database expert, which is already a fairly sophisticated group of people. And that's where I came across some of the problems of, say, executing bitemporal queries, how most databases sort of just to throw their hands up and give up. Most databases don't really support features, which we'll talk about, like as of joins. And you can shoehorn some of those. But you pretty much will get pretty lousy performance in executing them because the databases aren't really designed for that. Time series databases are a whole nother area that is getting more popular, but typically, from what I've seen, a lot of time series databases mostly deal with observability data, where the issues are more to do with efficiency and cost effectively storing large amounts of fairly low value data, in which dropping a data point or two is not frowned upon if it leads to greater cost efficiencies. And it's a reasonable trade-off when you're talking about something like observability data, right? You have lots of most data points. Most of them are just don't matter, right? You really just want to understand the shape of the data and really understand when you are deviating from some expected norm. Um, the data is very different from a traditional database. A traditional OLTP database, you have about 100 times as many reads as you have writes, right? This is a standard rule of thumb. In observability workload, you have about a million times as many writes as you have reads, because most of the time you're writing something down and everything is normal and nobody cares and nobody's going to look at it, and it's eventually going to be garbage collected out of the way, right? And entirely appropriate to make completely different set of trade-offs. But that leaves people who want to do precise, exact, complex calculations over time series data lacking, because the traditional OLTP databases aren't really geared to serve that domain, and neither are what people call time series databases, because they're really made for this observability lossy data. I'm quite fascinated by this because a stock ticker is a classic example of a thing that moves with time, in which lots of people are willing to pay lots of money to get precise calculations very quickly and efficiently. And yet, it's not something that the traditional database developer or enthusiast really knows a lot about. And I find it very exciting. So excited to be here and excited to talk about XTDB. So with that, I'm going to throw it over to James to introduce a little bit of XTDB and tell us what it is about and what it's really solving.
Yeah, thank you very much, Arjun. Yes, XTDB, it's an open source bitemporal database. As I've been development for about sort of 5 years now, and we're shortly about to launch a V2, which is a significant improvement on our V1. What V2 brings is a much broader reach. So we are now able to be queried through the SQL 2011 by temporality functions. And it's queried through the Postgres wire protocol as well. So any Postgres tooling that you might have will in theory connect to XT. So we're already opening XT up to a wide range of your BI tooling and your existing language drivers, and all of the other sort of parts of the SQL ecosystem that have built up over the last 51 years now of SQL. So XT, in terms of where it fits, I mean, you spoke a lot there, Arjun, about the different trade-offs that different databases might make. In terms of where XT fits into those, we are broadly speaking going HTAP for one. So HTAP is hybrid transactional and analytical processing. And so, whereas previously you may well have seen sort of either HTAP transactional databases or OLTP transactional databases or OLAP analytical databases, like databases that focus on one or the other. XT tries to shoot here for a middle ground where we are good enough in both camps to remove the cost required to be migrating data between the two, and the inconsistencies that come with it. So while we may not sort of keep up with Postgres on the OLTP end or Snowflake on the OLAP end, if we can remove the need for people to be writing these complex ETL jobs, we consider that a real value for the systems of record that we're targeting.
So just a little bit to wrap my head around this, because there's many flavors of HTAP, and there have been many attempts to make many kinds of HTAP databases. I'm just going to give you a dumbed down framework that I use to think about the various camps. So before I even get there, one important thing is XTDB is also immutable, correct? So you can't really delete, or when you do a delete, it still maintains the history that this thing was written and then was deleted. And so as of this time, which again we'll get to, that as of is a key way in which we think about everything. But you never lose the record that this thing actually existed in the past. Is that correct?
Yeah, that's correct. I would make, because I did have one person ask me about immutable databases, and they came at it with a slightly different sort of perspective. In the an immutable database, like a data warehouse, for example, where the average user isn't going to be writing into it at all, and that's not, just to be clarified, that's not what XT is. Like, you can make inserts, updates, and deletes on XT.
Right.
So that's the transactional side. But as you say, those inserts, updates, and deletes are the record of them is never removed.
One of the things that I think of the core competency of OLTP databases, let's talk about a traditional OLTP database like an Oracle or a Postgres, right? Its job is to allow the developer to maintain data integrity through having sophisticated transaction support that allows the user to do some kinds of reads and then decide whether a write they want to commit a write and then attempt to commit a write, and if it can't be done atomically, the database should throw the whole thing out. And the reason this is valuable, I canonically think of the example I think of is Ticketmaster, right? Like the new Taylor Swift show has come out. There are 10,000 seats available in the stadium. Each one of those has a name or a number and a row and a column. Everyone's flooding the website to try and buy that very second. It is an absolute disaster if the back end allows two people to successfully think that they have both purchased seat A124. Right? That is the canonical disaster that an OLTP database is designed to solve, which is the admission control. You want a very specific set of constraints. Only these things can succeed, and it is better to fail the query and abort the query atomically such that everybody knows that this query did not commit than to allow two things to commit where only one should succeed. That requires a tremendous number of data structures, bookkeeping, and that's primarily what an OLTP database is designed around. There's an easy way to get around this, which is to simply force everybody through a single queue. And you could, at this point, completely crater the number of transactions that will be processed per second. And so the real art form here is to do this at high throughput. So lots of people can get in and get out and get their transactions processed. So you have a very, very highly concurrent, highly performant system that nonetheless enforces all of this. An OLAP database is not going to do this. An OLAP database pretty much exists in the world where somebody upstream has already taken care of this problem. And we are being presented with the set of transactions that did happen. We know nothing about the transactions that were attempted and were aborted. Does not matter. That's all taken care of upstream. We are presented with a transaction with a set of completed and valid transactions. In fact, most OLAP databases will not even check. Right? So if you have, for instance, a constraint that must be satisfied, like a foreign key constraint, they will not even bother to check because they assume that the upstream system has ensured that this has never been violated. You could do this in a batch fashion, so in an ETL fashion. So once a day, you get a list of all the transactions that completed yesterday, new batch a day. You can do this in a streaming fashion, right? So Materialize occupies this space, right? You can give it within milliseconds of the transactions committing. You can give it the completed transactions, such that you can do something more real time. But this is, the task of admission control has been pushed upstream. Does XTDB take on this challenge, or does it assume that the set of transactions are non-conflicting and have been the conflicts have been resolved upstream? That to me is the key question between OLTP and something else.
So again, yeah, we do actually shoot for a middle ground here, as it stands. So XT is very much based on the idea, first popularized as far as I can tell by Martin Kleppmann, of turning the database inside out. And he gave a great talk a few years back, which we can probably link to with the in the show notes or whatever it happens to be. But essentially, the idea behind turning the database inside out is that you focus on the write ahead log as the main entry point of data into the system. And XT does this through its integration with Kafka, primarily Kafka, which for us is responsible for sorting out that ordering problem. So Kafka solves a non-trivial sort of distributed systems problem of the total ordering of sort of consensus of total ordering of messages, and so we lean on heavily on that in order to get that total ordering. So if we were
somebody is doing the conflict resolution upstream of that, because once the total ordering exists, then that problem has to have been taken care of.
It does. So we have the total ordering from Kafka, and we then have a number of primitives within the database that a user can use that, given a total ordered stream, will then give them those kind of consistency guarantees that you were referring to there. So we have in our transactions in XT, you essentially ship the whole transaction off to Kafka. You serialize it onto Kafka, and as part of those transactions, you can specify preconditions. So I can say, in your Ticketmaster example there, I can say assert that seat A124 hasn't yet been booked, and because I know I'm the only person chewing through the Kafka log at that point, that's when we get the conflict resolution between the two. So the user, when they check the result of that transaction, will see, yeah, my transaction succeeded. I've managed to book seat A124, or no, it failed because the precondition didn't hold when the transaction actually came to be evaluated.
Perfect.
And we can still get a really decent amount of performance on that. That sort of, I mean, a single thread. I mean, I hear you talk about sort of cratering the performance, and true, relative to a sort of a heavily parallelized system, it obviously does. But you can get one hell of a lot of performance out of a single thread these days. So
Yes.
we're looking at sort of 100,000 or so like entities per second coming through off a Kafka log. So it does, which obviously we'd like to scale that horizontally at some point. But for now, that is a decent limit.
I'd love to hear a little bit of a sort of canonical example that you folks use, a canonical customer, fictitious or or not, use case where XCDB is the sort of perfect fit.
Yeah, I mean, reflecting on your opening, I think the nature of databases, they always evolve in response to workloads. So something like KDB evolved in a context where people were just streaming in tick data, and they needed the fastest possible system for that. And I think XT's context is there are transactions happening out there in the world. There are trades being executed, and you want to represent and capture that information in XT. But then there are some transformations and decisions that are being made by business users on top of those transactions. And there's all kinds of reference data and other feeds. And you want to be able to provide users with a reliable system with atomic writes, which can integrate data from many sources. Most of those sources are, transactional in their own right, but XT sort of shadowing them and able to prove what was known at any point in time by those decision makers. So the approaches that are often taken is to have lots and lots of reports flying around, like emails with spreadsheets, or maybe huge databases with very, very frequent backups and snapshots in place. And that's kind of the state of the art that we see in the world a lot, is in a financial context, people firing around spreadsheets. These aren't necessarily enormous databases. We're not talking about petabyte scale, but they are complicated, maybe deeply nested JSON structures representing all kinds of financial models and products, which are evolving over time. And maybe those transactions that are sort of generating those records of those trades are happening elsewhere, but maybe they're also in our system, and we want to be able to capture and model that accurately without worrying about constraints if we don't want to. But if we need constraints, we have the tools there to implement them.
One of the funny jokes that I can't recall who exactly told me this one the first time, but it has stuck with me, and I've used it so much. Most businesses don't have big data. But they can inadvertently generate big data, even when they don't strictly need to. And a good example of this is you have some moderate size, I'm not saying small data, a moderate sized data set that is evolving over time. But in order to prove various things that the business might need to prove, you can take a snapshot of that database every hour. Right. And if you do this naively, you can generate big data out of what is not really that much data, because the sum of all the snapshots that you've taken over the preceding years can become ginormous. Right. Now, of course, you don't actually, strictly speaking, need to store these things as separate snapshots. Nevertheless, a lot of businesses, for compliance, for auditability, produce these snapshots. And what I'm hearing is, there can be a better way if that underlying data set simply strictly keeps the immutable log of all the changes and is queryable at any point in time in the past, without needing to naively take a file system backup every so often and store it on a separate object storage blob.
Yes,
Yeah,
yeah, absolutely. And oh, sorry, Jeremy.
well, I was just going to say yes, absolutely as well. But where people do then have these, like we call them coping mechanisms, these ways of coping with this problem, they end up proliferating data in lots of places, and then the moment they want to run like a new query, they then have to figure out, well, what is all this data? Where are all the versions of it? What were the schemas at the different points in time? And they then hand that problem over to probably a separate team who have to build another data warehouse, data lake infrastructure to pull in that data and reprocess it and remodel it. And that's just absurd, because we think a lot of this movement of data around is because general purpose databases aren't good enough. Basically, that's the real argument.
I consumed a large quantity of lawyer fiction as a child, so I think of the canonical question in my mind that one really needs a system like XDDB is to answer the question, what did you know and when did you know it? Because the when did you know it is the hard one, because and is often very, very crucial to understand and to prove some lawful or non-lawful behavior was because something that you did when you didn't know a fact can become a very bad behavior if it happened after a fact. It's easy to think of, a compliance situation where you are obligated to act or obligated not to act, depending on what information you do know.
Yes, and I mean that's one of the great benefits of bitemporality here is that you can then make this distinction between do I or do I not want to know about corrections, like subsequent corrections to the data. So
I would love to get an introduction to bitemporality. So for any listener, this is again a concept that I learned very, very late. I want to say I was working on databases with a PhD for close to a decade before I really was introduced to this. So it will not be surprising to me that this will be new to a lot of people.
Right. So the way I tend to think about bitemporality is if you build it up from what existing databases largely have. So if you look at a database like Postgres, for example, it's by default it's completely atemporal, has no knowledge of any kind of time or anything like that. So when you make an update to Postgres, you update it in place, and you essentially scratch out the previous record, and you insert and you update the new value in the row, having mutated the old one. To move towards bitemporality, we'll then add one time dimension in, which is system time. And so what you then do is you say, right, okay, when I make my update, I want to then remember the previous version. So in Postgres, I may be implementing that either with like an updated at on the table, like I might be putting a version number, and then every time that I query that table, I then need to remember, okay, I need to be like filtering it by the latest version for this particular table. Or I'm doing it with audit tables, like history tables, and I'm saying that every time there's an update on this table, I've got a database trigger, which will copy the old row over to the history table before it gets overwritten. So that's Unisem. Adding in the concept of system time then means that your database can then go back to a point in time and show you what the data was at that point. Adding in the second time, then the by part of bitemporality is then valid time, or you may have heard this called application time, domain time, business time. Goodness, we've got too many words for
Event
things.
time.
So,
event time is the one that I've mostly heard.
Yeah, there's so many of them. I think in the bitemporal literature, it's all valid time, and in the SQL spec, it's application time. So yeah, I mean, as usual in our industry, we've not settled on a term for this thing. But what you're doing with valid time or business time is you're saying that outside of system time, because I can't change system time. That's what the database takes care of for me. Outside of system time, I still want to be able to correct the past, or I still want to be able to schedule an update in the future.
And this is
Like
an
my-
intuitive thing to wrap your head around, which is that messages are sent at some time and they may be received at a different time for whatever reason. And it's not just network delay or things like that. It's just that systems, the world is a contract may have been executed with a firm handshake by two people in fancy suits at 11:04 a.m. But then only called back into the back office a couple hours after the martinis were consumed to celebrate that deal, right?
Yeah.
That the database will only get updated at that system time. It cannot go back and change the time at which it's entered. It's very, very intuitive to understand, at 11:04, this happened and it was entered in the database at 2 p.m.
So this is exactly what the differentiation between the two timelines in bitemporality, the two temporal dimensions. But what that then allows you is the ability to ask two types of questions. So I'm looking at the history of this book, for example, this order book, and I might see this 1104 order, and I now need to know what the state of this order was. Let's say that over this period of time, the order has been altered or amended, whatever it may be. If I want to go back in time and still see with corrections, so as best known, I want to see we had something wrong with the data originally, we corrected it. When I go back in time, I actually then want to see as best known, what do we now know the state of that to be? If I'm going back through, let's go back to your lawyer case here. If I'm going back in an audit type use case, I may want to see exactly what the system showed at the time. So we didn't know about that correction at the time. And that's why I made this decision that I made. That's why my risk got out of whack, whatever it may have been.
Right.
So that both of those are completely valid use cases for looking at that data.
Right. And I just want to flesh out your use case a bit to just add some intuition here. There are many organizations in the world where over a set of transactions are computing hundreds of different functions. What is my exposure to this? What is my exposure to currency? And they have various limits. And if these limits are exceeded, they've contractually promised people these limits won't be exceeded, so something must be done there or reported as mandatory reporting. Or B, some corrective action needs to immediately be taken. We need to immediately tell the traders to dial back the risk that they are taking or make some offsetting trades or fix it. And everyone really wants to make these corrections happen as fast as possible, right? And you could have hundreds of these queries that in parallel have to be maintained and computed as this sort of history is changing, including the arrival of late data, because there are 5 concurrent exchanges on which all the things are being traded, in which that are geographically dispersed, and they all want to sort of have a collective view of the sum of all of their activities, and then compute all of these functions. That's sort of what I have in my head as a sort of running example here.
Yes, yeah, absolutely. And in those situations, it's really crucial that you can take a snapshot at a point in time, and use a consistent view of the world. Because I mean, if you do have all of these different data sets coming in, and they are updating completely concurrently, the ability to take at any one point in time and say, right, okay, I want to just take a snapshot here. I can then run multiple queries against that. I can then run multiple queries against that, and I know that my underlying data set is at a consistent state.
One as we have here in the title, one of the things that is very challenging to execute in most databases is the as-of join. Can we introduce the as-of join? What is an as-of join, and when would one want one?
So as of join then is if you're looking across multiple of these tables with bitemporal history, and you need to know that between these tables, if these tables are being updated at different times, you may well want to see an overlap of when these two particular things are true. So let's say, for example, if I'm, let's say I've got, my mind goes blank, doesn't it, when you're thinking of examples? So the example I would look at would be, for example, if I've got two people who are working together. I've got my employees table. I want to find out when two different people overlapped. I might well take that table twice. That'd be a self join. And then I would say, give me all the people who worked with this person for the time that they worked here, or give me generally speaking, whenever these two things happened at the same time, or were true at the same time.
Another one that I have in my mind is like computing where my packages were shipped in Amazon based off of my address history and my order history. You can't just look at my address as it currently is, because I update that field, or not every minute, but my Amazon history goes back decades. I've updated it a couple dozen times. And that join has to take into account the time at which the order was made and shipped, and the as of joined with the address, but as of the time in history. These and you could in the high performance case where you have a lot of changes happening. Another one is stock trades and prices to compute sort of execution costs. If you're thinking about hypothetical trades that you can or cannot make, it really depends what the price was at that time. And as you get arbitrarily more complicated, what the order book state was at that time. So how much liquidity was there? How many outstanding orders were there in the past, which changes quite rapidly.
Yes, Jen, and this was something you worked on quite significantly at Materialize.
Materialize does not have very good as of join support. It really focuses on incremental view maintenance, doing it correctly and efficiently for complex queries, but not with historical look back.
Right. Okay.
It is possible to do some historical look back, but the system's really designed for performance with as of now, essentially.
Right. Okay. Yeah.
Going back into the past requires, and this is sort of requires dedicated, I say, design choices in the indexes that are temporally aware and sort of stay temporal. So a good example is why does a traditional OLAP database not perform very well on an as-of join? One, because they're mostly they're indexes, they're are hash indexes that really allow to split your data across and get efficient parallel query execution. This is not compatible with an as-of join, because an as-of join is not a precise hash join across two tables. It is a get me the most recent, but where there is no more recent row that matches my row, right? So I say, I want to make a trade at 11:06 a.m. Well, I want the price. You have some arbitrary list of price updates that may or may not happen. I need to know the most recent one that is less than 11:06, and it has to be the most recent one, and not invalidate. And that is not a hash. You can't hash across that. You need an ordered index data structure that you are able to efficiently join across to potentially very large, very fast moving tables. So
Yeah.
I'd love to dig a little bit into the internals of XDDB. What makes that efficient?
So in XDDB, our primary index is sorted both by the entity ID and then also the system time of the update of the event that came in. And so this is one of the main reasons behind XT existing, really. If we take a step back and look at that, is that if you do want to build this on top of an existing relational database that isn't temporality or isn't aware of temporality, you're essentially, as you say, sort of fighting with the existing structures and indices that are there. Whereas what we did was we spent a long time going through identifying what temporal data looks like in practice. And so I break that down into a number of different sort of dimensions, if you like the cardinality of the data, whether it's whether it's sort of the number of distinct entities within a table, the sorts of updates that might happen to those entities. So are they, is it like a really fast updating entity, like a stock price, for example, or is it a more moderate changing data, like a user profile or an employee record? And also, what sorts of timeframes are those updates looking like? So we then went through, and from that built up the XTDB index that is then responsible for getting the temporal performance that we get from XT. So if you are, and let me share my screen over here. If you are doing this without a, let me pop this up. How's that? So this gives a rough idea of what XTDB is storing for a given entity. So I'm making 3 updates here to my user record. I'm making 2 updates that are relatively normal, so these are as of now. But at T4, I've decided that I actually need to make a retroactive correction to my data. Now, if you don't have a bitemporal database, what you're then required to do is maintain the history table as you go. So when that second update comes in, I'm actually updating a lot of rows. If I'm maintaining the bitemporal columns here, system time and valid time. And likewise here, once I have my retrospective collection, you can see the amount of different rows here that are being updated, and so even back in time. So in a traditional database, this actually involves quite a lot of row churn. And so if you're looking at Postgres or equivalent, you're having to go back, read plenty of data every time you're making a write. What happens with XT is that we actually only store the event data here. So this is the quickest possible write that we can make, is appending to an append-only log. And so what I'm doing is every time I get an event in, I'm appending what time the event happened, the period of valid time that it affects, and the data of the document. Our trick with XT is that we can then filter out these events. We partition the index in such a way that I can very quickly narrow it down to the events that are interesting for a specific query. So in SQL over here, I will, as a user, I'll specify the valid time that I'm interested in and the system time I'm interested in. Most of the time, I'll default this to as of now, as you say, Arjun.
Right.
Like the overwhelming majority of queries are as of now. But again, because of the way we sort and partition these events, I naturally filter out the vast majority of the historical data, and so I don't have to look at that. So again, partitioning.
One point I will bring up here is that most transactional databases use a technique known as multi-version concurrency control to gain higher throughput while maintaining strong isolation guarantees, whatever the actual isolation guarantee is, which means that they do have to maintain multiple versions. And they do have to do some logic like this. The difference between a system like XTDB and a multi-version concurrent OLTP database is a multi-version concurrent OLTP database really only maintains a few versions before it no longer becomes efficient or tractable for the database to go. So you can think of it as in the face of fast updates, where in the past, call it 10 seconds, there've been less than 100 rough order of magnitude of updates. They have to do logic like this, but it really sort of falls apart because they don't have the indexes that can really go all the way back to the start of time. The real value of XTDB is that this is carried out all the way up to the very first transaction that occurred in the database at the start of time.
Exactly. Yeah, and even MVCC, even when you've got very sort of, even when you've got very few updates, you're still having to keep track of the overhead of MVCC. So you're still having to keep track of what transactions are in flight, what versions each of those transactions can see, and whereas when you're appending to a log, it is the fastest write you can make. Because you're writing to the end of a file, whether that be in memory or spooling that out to disk. So we actually do very little of this by temporality at write time.
But that does. So one of the is there are no silver bullets here, right? Like there are trade-offs no matter which way you slice it. There's an
Yeah.
excellent system for doing as of joins, for doing immutable to queries over an immutable log, but you do have to give something up, right? Because there's just fundamental constraints here. And I'm trying to wrap my head around what it is that XCDB is bad at, because it has to give up that capability in order to get this other capability. Which I'm going to speculate here, but I'm really interested in your question, in your answer rather to this question. Um, I'm going to speculate that it is that you can't really do complex transactions to read the state of the log, compute some result, and then decide to do a write at that exact same point in time conditionally based on the results of, which is what a traditional OLTP SQL database really shines at. So if you look at a TPCC query, it's like, give me the state of the orders, the inventory, this, that, and then I'm going to make some computed result and then choose to do an insert, and then I'm going to commit all of this, and all of this should be valid and executed at the exact same time step. And you might have to keep some MVCC bookkeeping to do that efficiently and concurrently. You can't do that because now you have a log, and that log, you can read the state of the log at T1, and then you can maybe do a write that'll go back into the log, but you can't do that write as of T1. Is that correct?
So XT doesn't have the notion of interactive transactions in the same way, and that's the big trade-off that we've chosen here.
Yes.
So to do those kinds of things, you need to be able to essentially, as I said earlier, like shipping your transaction off to our Kafka log.
Right. So
What you'll do if
you also mentioned that XT is Postgres compatible or Postgres wire protocol compatible and has SQL. I often think of this choice of having interactive transactions and sort of baking it in at such a fundamental level to be the original sin of the SQL spec, because it has caused us so much heartache as implementers. And I agree with this trade-off you've made, which is we walked away from that, which is what really allows you to get all. And if people want interactive transactions, they can go find a different database system that will give them that. But how do you, on the protocol level, deal with the fact that you don't have interactive transactions? And so much of the tooling that speaks Postgres wire protocol sort of implicitly, there's a whole bunch of tools where like they'll just wrap everything in this begin end transaction block, for example, or throw in some introspection statements. And how do you deal with that?
They don't tend to mix. In our experience, at least, of the tools we've looked at, they don't tend to mix writes and reads within the same transactions. Not the tooling side of things, at least. So we can, when a transaction is opened, and you can use sort of Postgres, not sort of normal transaction management with XT. When a transaction's opened, we keep a track of what you're doing with that transaction. Like, are you making inserts and updates, or are you making selects?
So you can have multiple inserts and updates in a transaction block, and you can have multiple selects. You just can't mix and match them.
Correct. Yeah.
That seems like a very reasonable compromise.
Yes, I mean all the kinds of there's a lot of the sort of the usual interactive transaction use cases that you might have, which you can still do with SQL DML. So, for example, within an update, like an update or a patch will get you a decent amount of the things that you tend to do with an interactive transaction. Also, if you're looking for preconditions, we've added in an assert primitive, which says I want to assert that the state of my database is this at this given time. So there is a bit of a compare and swap available there. Now, obviously, as a user, and you were talking about trade-offs there. As a user, you've then got to be dealing with that compare and swap. What happens if that compare and swap fails? Which is something that MVCC you can just do. You can just do naturally. I mean, the transaction will still roll back in MVCC, but it's less likely to happen.
So, I think it's a really important sort of area to look at what does XT not give you, and if you're looking for high concurrency transactional workloads, we're not there right now.
Yeah.
But I think one of the insights we've taken away from people like Rich Hickey and all the other let's call them immutability thinkers is that you can figure out different scaling patterns to make it work. Right. A lot of transactional databases were built around this promise of being able to have infinite scaling without really any downsides. But naturally, you always have partitionings, and a lot of those databases have now been almost superseded by things which then just shard on top of those, that sort of worldview of that model. And I think there's a really interesting overlap with incremental V maintenance as well, because the moment you have many logs, you want to be able to sort of use sharding in a sort of very controlled way, expose that to the users, and then you're back in this sort of how do I join across these data sets. But if you make those semantics explicit to users, then users will actually appreciate the scalability of the database, as opposed to being like, oh, my Postgres box is too small, I have to move it over to another one because my data set, or my data model is too coupled. So yeah, we're sort of big believers in immutability and functional programming, and that's sort of driven a lot of the design. But yeah, conscious you have a hard stop, so thank you, Arjun, for your time. Yeah, curious if you had a closing.
Thank you so much for having
piece
me.
Of advice.
I'm very fascinated by XCDB. I think it's a wonderful project. I'm a fan of bitemporal query execution. I think there's a lot of times when I've encountered these queries in the wild, people do horrendous things to make up for the fact that their database does not allow them to execute these things correctly. I would say I'm first and foremost a fan of correctness and correct execution, and again, totally accepting that there are domains where like observability, where that is explicitly not that's not part of the spec. You don't need it. It's horrendously expensive. There's no point in storing all of your time series metrics data and computing over it. That's fine. But then where people get themselves into trouble is when they use tools that are designed for that world, in a world where it does matter, and then find that they've lost millions of dollars, or worse, expose themselves to being non-compliant in some way. So excited to see the progress you have all made. Very excited for the launch of XTDB2, and congratulations, and good luck with the launch.
Thank you, Arjun. Pleasure to talk to you.
Thanks.
Cheers. Thank you very much.
Thank you.
I'm assuming that's Jeremy cutting the recording part. Thanks very much, Arjun. That was very,